You know, there's a recurring narrative in science fiction and increasingly in serious discussions about humanity's future. The idea that Earth is somehow dispensable or temporary, that we're approaching a time when we might abandon our home planet and relocate to space stations or Mars colonies or generation ships heading to other stars, that humanity will transcend its planetary origins and become a truly spacefaring species no longer dependent on Earth for survival. This vision appears in countless novels and films, in the plans of billionaire entrepreneurs investing in Mars colonization, in academic papers about interstellar travel and space settlement, in popular discourse about humanity's destiny among the stars. It's become almost conventional wisdom among space enthusiasts that Earth is the cradle, but eventually we must leave the cradle and venture into the cosmos. And I'm going to tell you why this entire premise is fundamentally wrong. It is impossible for humanity to abandon Earth, not difficult, not challenging, not waiting for better technology, but literally impossible because of the inextricable biological connection between humans and Earth's biosphere, because our bodies and minds evolved over 3.8 billion years in this specific planetary environment and are adapted to it in millions of ways, both obvious and subtle, because we are not separate entities that happen to live on Earth, but are integral parts of Earth's ecosystem that cannot exist independently. Our biology traps us, not metaphorically, but literally. We are bound to Earth by evolution and biochemistry and physiology and psychology in ways that cannot be overcome through technology or engineering or willpower. This isn't about lack of propulsion or energy or resources. It's not about the challenges I've discussed in previous contexts regarding the difficulty of reaching other worlds or maintaining life support in space or building self-sustaining colonies. Those are real barriers, but they're not the fundamental barrier. The fundamental barrier is that humans are Earth organisms, products of Earth's specific evolutionary history, adapted to Earth's gravity and atmosphere and temperature and chemistry and day-night cycles and seasons and countless other features of this planet's environment. And removing us from this environment creates biological and psychological problems that cannot be solved because they're not engineering problems, but mismatches between organism and environment that are intrinsic to what we are. We are condemned to live and die here, not through lack of ambition or technology, but through biology, through the fact that human bodies require Earth-specific conditions to function properly and cannot be adequately protected from or adapted to alien environments without ceasing to be recognizably human. And this biological trap is permanent. It's not something future technology will overcome, because overcoming it would require redesigning human biology so completely that the resulting organisms wouldn't be human in any meaningful sense. They'd be post-human entities descended from us, but alien to us. And even if we created such beings, it wouldn't constitute humanity abandoning Earth, but rather humanity going extinct and being replaced by its engineered descendants. Now let me be precise about what I mean by abandon Earth, because there are different scenarios and not all are equally impossible. When I say humanity cannot abandon Earth, I mean we cannot establish large self-sustaining off-world populations that are independent of Earth's biosphere and that maintain human biology and psychology as we know them. We cannot relocate significant fractions of human population to space or other planets permanently without catastrophic health consequences. We cannot survive the death of Earth's biosphere through moving elsewhere because we need Earth's biosphere to live, and we cannot transform into a species that primarily lives off-world, with Earth becoming optional or obsolete. I'm not saying we can't send small numbers of people to space for brief visits. We've done that successfully for decades with astronauts visiting space stations and the moon, nor am I saying we can't maintain small outposts off-world for scientific or strategic purposes, similar to Antarctic research stations. We can and probably will. What I'm saying is that these activities don't constitute abandoning Earth. They're marginal extensions of Earth-based civilization that depend completely on Earth support and that house tiny fractions of humanity for temporary assignments, their Earth activities conducted in space, not independent space societies. True abandonment would mean substantial populations, thousands or millions or billions of people living permanently off-world across multiple generations, being born and raised and living entire lives without returning to Earth, maintaining themselves independently without continuous resupply from Earth, and eventually persisting after Earth becomes uninhabitable from asteroid impact or climate catastrophe or the sun's evolution billions of years hence. This is what's impossible, and it's impossible primarily because of biology, not engineering. Let me start with the most fundamental biological barrier, which is gravity, because humans evolved under Earth's 1G gravitational field, and our bodies are exquisitely adapted to this specific gravitational loading in ways that are essential to our physiology and that cannot function properly under different gravitational conditions. Every system in the human body has been shaped by evolution to operate under 1G. Our skeletal system must support our body weight against gravity. Our muscular system must move our bodies against gravitational resistance. Our cardiovascular system must pump blood upward from legs to brain, fighting gravity. Our vestibular system senses gravity to maintain balance and spatial orientation. Our developmental processes from embryo through adulthood depend on gravitational loading to form bones and muscles properly. In microgravity or reduced gravity, these systems malfunction in ways that cause progressive damage. We've learned this through decades of space station operations where astronauts experience bone density loss at rates of 1 to 2% per month despite intensive exercise, muscle atrophy, even with resistance training, cardiovascular deconditioning, where the heart weakens because it doesn't need to work as hard without gravity, vision problems from fluid shifts to the head, increasing intracranial pressure, immune system dysfunction. These effects accumulate over time, and while some are partially reversible upon return to Earth, others cause permanent damage. For permanent space settlement, the consequences are catastrophic. People living their entire lives in microgravity or low gravity would develop skeletal systems too weak to function in Earth gravity. They become adapted to the reduced gravity environment, but unable to return home. Children born in space would develop abnormally with underdeveloped bones and muscles because gravitational loading is necessary for proper development. Their bodies would be shaped by their environment, creating a population physiologically distinct from Earth humans and probably suffering various health problems from developmental abnormalities. Mars with 0.38 grams provides some gravitational loading, but probably not enough to maintain human health long term. We don't know precisely what minimum gravity is required because we've only studied microgravity and 1G, but given that even 6 months in microgravity causes serious problems, it's likely that Mars gravity is insufficient for healthy development and indefinite habitation. And for destinations with lower gravity like the Moon at 0.16 grams or asteroids with essentially 0G, the health consequences would be even worse. The only solution to this problem is artificial gravity through rotating habitats that use centrifugal force to simulate Earth's gravitational field. But this is extraordinarily difficult and expensive at scales needed for large populations. You need massive rotating structures with diameters of hundreds of meters to avoid uncomfortable Coriolis effects. These must be built in space and maintained reliably over decades. Any structural failure or imbalance causes the rotation to fail and gravity disappears. People living in such habitats would depend completely on the engineering working perfectly continuously with no failures. And even with artificial gravity, you face the problem that anytime people leave the rotating habitat for activities outside, they experience microgravity and the associated health effects. If you're living in a rotating space habitat but spending significant time doing EVAs or traveling between habitats or working in non-rotating areas, you still accumulate microgravity exposure and the health consequences that come with it. So artificial gravity is a partial solution at best and an extremely difficult engineering challenge that adds enormous cost and complexity to space habitation. The gravity barrier means that humans cannot live healthily in space or on other planets without artificial Earth-equivalent gravity. And providing this requires such enormous infrastructure that it limits space populations to relatively small numbers in expensive habitats that must be continuously maintained. We're not talking about terraforming Mars to make it habitable. Even terraformed Mars would have wrong gravity and would be uninhabitable without protective equipment or biological modification. The gravity problem is fundamental and can't be fixed by changing the atmosphere or temperature. Now let me discuss the atmospheric and pressure requirements, which create another absolute barrier to abandoning Earth, because humans require very specific atmospheric conditions to breathe and survive, and these conditions exist naturally only on Earth. We need oxygen at partial pressure of about 16 to 21 kilopascals, roughly the range from high altitude to sea level on Earth. Below 16 kilopascals, we experience hypoxia and lose consciousness. Above about 50 kilopascals, oxygen becomes toxic, causing oxidative damage to tissues. We need total atmospheric pressure around 100 kilopascals, 1 bar, to maintain proper fluid balance in tissues and prevent decompression injuries. Significantly lower pressures cause dissolved gases in blood to come out of solution, creating dangerous bubbles. Higher pressures increase dissolved gas concentrations, creating narcosis and toxicity risks. We need nitrogen or similar inert gas as diluent to prevent oxygen toxicity while maintaining adequate oxygen partial pressure. We need absence of toxic gases like carbon monoxide or hydrogen sulfide or sulfur dioxide above trace levels. We need appropriate humidity around 30 to 60% to prevent respiratory tract drying or condensation. We need temperatures roughly 15-30 degrees Celsius for comfort, though we can survive wider ranges with clothing and shelter. These requirements are very specific and exist naturally only on Earth. No other body in our solar system has naturally breathable atmosphere. Everywhere else requires complete life support, providing artificial atmosphere continuously. Mars' atmosphere is 95% CO2 at 0.6% of Earth's pressure. You can't breathe it. You'd suffocate from lack of oxygen and simultaneously suffer decompression injuries from low pressure. Even wearing a pressure suit, you're completely dependent on carried life support. Venus has crushing pressure and toxic atmosphere that would kill instantly. The Moon and asteroids have no atmosphere at all. The outer moons have cold atmospheres of nitrogen or methane that aren't breathable. Nowhere in the solar system except Earth provides naturally breathable atmosphere. This means humans living off Earth require artificial pressurized habitats with life support systems continuously maintaining correct atmospheric composition and pressure and humidity and temperature. These systems are complex and consume resources and energy and require maintenance and have failure modes that can kill everyone in the habitat within minutes if they fail catastrophically. We've been working on life support for 60 years of human spaceflight, and we still can't create truly closed-loop systems. The ISS requires regular resupply of oxygen and nitrogen and water despite extensive recycling. Losses accumulate and must be replenished from Earth. Scaling up to thousands or millions of people living permanently off-world requires life support systems that work perfectly reliably for decades with minimal maintenance and resupply. and these systems must process all human waste products, including CO2 and metabolic byproducts, and convert them back into oxygen and water and food. This is extraordinarily difficult because closed ecosystems are inherently unstable and prone to cascading failures, as Biosphere 2 demonstrated. Maintaining the delicate balance needed for human survival over long timescales might be impossible. So the atmospheric requirement traps humans in artificial environments when off Earth. We can never walk freely on another planet, breathing naturally. We're always confined to habitats or suits, always one equipment failure away from suffocation or decompression, always dependent on technology working perfectly. This is not true abandonment of Earth, but rather bringing a piece of Earth's environment with us in the form of life support systems that must continuously recreate the atmospheric conditions we evolved to need. Now let me discuss the radiation environment, which creates yet another biological barrier that prevents humans from truly abandoning Earth and living permanently in space or on other worlds. Earth's surface is protected from dangerous cosmic radiation by two crucial shields: the magnetosphere, which deflects charged particles from solar wind and cosmic rays, and the thick atmosphere, which absorbs gamma rays and high-energy particles that penetrate the magnetic field. Together, these shields reduce radiation exposure at Earth's surface to about 2 to 3 millisieverts per year from cosmic sources, plus some additional exposure from terrestrial radioactivity. This is a level that biological organisms have evolved to tolerate and repair. Our DNA repair mechanisms handle this background damage rate without accumulating mutations at harmful rates. Beyond Earth's protective shields, radiation exposure increases dramatically. On the Moon's surface, annual dose is about 380 millisieverts, roughly 100 to 150 times higher than Earth's surface. On Mars' surface, it's about 200 to 300 millisieverts due to some atmospheric shielding, but no magnetic field. In interplanetary space during solar minimum, it's 400 to 600 millisieverts per year, and much higher during solar particle events when dose rates can spike to lethal levels. These radiation levels cause serious health consequences over time. Increased cancer risk is the most obvious. Exposure to 200 millisieverts increases lifetime cancer risk by about 1 to 2%. So someone living on Mars for 20 years accumulates 4 to 6 sieverts. Exposure increasing cancer risk by 20 to 40% above baseline. This is completely unacceptable for general populations. Beyond cancer, radiation causes other health problems: cataracts from lens damage, cardiovascular disease from vascular damage, central nervous system effects, including cognitive decline and memory problems, immune system suppression, accelerated aging from accumulated cellular damage, potential genetic damage affecting offspring, though this is less well understood. These effects are cumulative and irreversible. They worsen with duration of exposure. People living their entire lives off Earth would suffer severe health consequences and shortened lifespans. Children born and raised in high radiation environments would experience developmental problems and elevated cancer rates throughout their lives. The only protection is shielding, but effective radiation shielding requires meters of material to absorb high-energy particles. You need about 2 to 3 meters of water or regolith or equivalent material to reduce radiation to Earth-like levels. This means building habitats underground or covering them with massive amounts of shielding material, adding enormous mass and construction challenges and cost. On Mars, you could potentially build underground using lava tubes or by burying surface habitats in regolith, but this creates bunker-like living conditions without natural light or views, psychologically problematic for long-term habitation, as I'll discuss later. In space habitats, shielding is even more challenging because you need to provide the shielding mass, which must be launched from Earth or mined from asteroids. Either option is extremely expensive. A rotating habitat for 10,000 people with adequate radiation shielding, masses millions of tons. Getting this material into space or processing asteroid material to create shielding requires enormous energy and infrastructure and time. And you still can't fully protect against the highest energy cosmic rays, which penetrate any practical amount of shielding. You can reduce exposure but not eliminate it. Some researchers propose using magnetic shielding to deflect charged particles similar to Earth's magnetosphere, but creating magnetic fields strong enough over large enough volumes to protect habitats requires enormous superconducting magnets and power systems. This is far beyond current technology and might never be practical at scales needed for large populations. And magnetic shielding doesn't protect against neutral particles or gamma rays, which require physical shielding anyway. So the radiation barrier means that humans living off Earth face continuous health damage that accumulates over time, shortening lifespans and causing suffering and disability. Children born off-world face developmental risks and lifetime cancer risks far above acceptable levels. Protecting against radiation requires massive infrastructure and confines people to heavily shielded underground or enclosed environments. There's no scenario where humans can live freely on other worlds experiencing their natural environments without suffering radiation damage. This is another way our biology traps us on Earth, where natural radiation protection exists. Now let me examine the nutritional and biochemical requirements that bind humans to Earth's biosphere in ways that are extremely difficult or impossible to replicate off-world. Humans are heterotrophs. We can't synthesize all necessary nutrients from simple inorganic precursors. We require a diet containing specific amino acids, fatty acids, vitamins, minerals. These must come from food, either plant or animal, and these foods must be produced somehow in space habitats. This seems straightforward initially. Just grow plants and raise animals in controlled environments, providing light and water and nutrients. But the practical difficulties are severe. Plants require specific light spectra and intensities to photosynthesize. LED grow lights can provide this, but consume significant electrical power. A person requires about 50 to 100 square meters of growing area to produce adequate food depending on crop selection and yield. For 10,000 people, that's 500,000 to 1 million square meters of growing area, all requiring artificial lighting. This is an enormous energy load on top of all other habitat energy needs. Plants also require water and nutrients, an appropriate atmosphere and temperature, and protection from pests and diseases. Managing large-scale agriculture in enclosed environments is challenging. Even on Earth, in controlled greenhouses, doing it in space or on other worlds with limited resources and recycling requirements adds layers of difficulty. Soil ecology is far more complex than just providing nutrients to plants. Healthy soil contains billions of microorganisms per gram, bacteria and fungi and protozoa and nematodes forming complex food webs that decompose organic matter and cycle nutrients and maintain soil structure and suppress plant diseases. Recreating functional soil ecology in space habitats is extremely difficult because we don't fully understand all the interactions and requirements. Attempts to create closed-loop agricultural systems often fail due to unexpected nutrient imbalances or disease outbreaks or productivity declines. Animals for meat and dairy require even more resources than plants. They consume plant calories and convert them inefficiently to animal products. You need roughly 10 kilograms of plant matter to produce 1 kilogram of beef. This multiplication of resource requirements makes animal agriculture in space prohibitively expensive in terms of space and energy and water. Most space settlement proposals assume vegetarian diets to reduce resource consumption, but humans evolved as omnivores, and completely vegetarian diets require careful planning to ensure adequate protein and essential nutrients. Compliance over generations is questionable, especially if cultured meat or other protein alternatives aren't available. Water recycling is critical because importing water from Earth is prohibitively expensive, and in situ sources like ice on Mars or the Moon require energy-intensive extraction and purification. Habitats must recycle water from all sources, including human waste and agricultural runoff approaching 100% efficiency. But perfect recycling is impossible. Water is lost to chemical reactions and leaks and imperfect recovery. These losses must be made up from somewhere, or the system gradually dehydrates. Accumulating water from ice deposits requires mining infrastructure and energy-making settlements dependent on continued industrial operations. The same recycling challenges apply to all elements essential for life. Carbon and nitrogen and phosphorus and sulfur and trace elements must all be recycled from waste back into forms usable by plants and humans. This requires biological and chemical processes that we don't fully understand and can't perfectly control, accumulating imbalances over time as some elements lock up in forms that aren't easily recycled, eventually requiring inputs from outside the system to maintain balance. This makes supposedly closed-loop systems actually open-loop, requiring continuous resupply. Beyond basic nutrition, humans have co-evolved with Earth's microbial environment in ways that are essential to health. The human microbiome contains trillions of bacteria in the gut and on skin and in respiratory tract. These microbes aid digestion, synthesize vitamins, train the immune system, protect against pathogens. Their composition is shaped by environmental exposure to Earth's microbial diversity. In isolated space habitats, the microbial environment would be much less diverse, dominated by whatever microbes the initial colonists brought and whatever can survive in the artificial environment. This reduced microbial diversity could cause health problems through dysbiosis, where microbiome composition becomes unbalanced. Studies of people in isolated environments like submarines and Antarctic stations show microbiome changes over time with potentially negative health effects. Scaling this to permanent multi-generational habitation raises concerns about whether healthy microbiome ecology can be maintained without continuous exchange with Earth's broader microbial environment. We might need regular influx of Earth microbes to maintain microbial diversity, creating another dependency on Earth that prevents true independence. So nutritional and biochemical requirements create multiple dependencies on complex life support and agricultural systems that must function reliably over indefinite timescales. These systems require energy and water and maintenance and are vulnerable to failures that could cause starvation or malnutrition. Humans off-world are completely dependent on these artificial systems maintaining Earth-like biochemical environment. We can't truly abandon Earth because we need Earth's biosphere functions replicated artificially at great cost and difficulty. Now let me discuss the circadian and seasonal rhythms that are deeply embedded in human physiology and psychology and that are matched to Earth's specific rotational period and orbital dynamics. Humans evolved under Earth's 24-hour day-night cycle driven by our planet's rotation. This cycle is encoded in our genes through circadian clock mechanisms that regulate sleep-wake cycles, hormone release patterns, body temperature variations, metabolic processes, cognitive performance. Essentially every aspect of physiology shows circadian rhythms synchronized to the 24-hour day. These circadian rhythms are not merely habits, but are genetically programmed biochemical oscillations involving thousands of genes and proteins. They persist even in constant darkness, showing their endogenous, not just responses to external light, but they need to be synchronized to the external environment through light exposure, particularly bright light in the morning. Disruption of circadian rhythms causes health problems, including sleep disorders, metabolic dysfunction, increased disease risk, cognitive impairment, mood disorders. Shift workers who work against their circadian rhythms show elevated rates of cardiovascular disease, diabetes, cancer, obesity. Other planets have different day lengths that would disrupt human circadian rhythms. Mars has a 24.6-hour day, which is close to Earth's and might be acceptable, though even 37 minutes difference could cause chronic misalignment. But Venus has 243-day rotation period. The Moon has 29.5-day day-night cycle. Jupiter's moons have days ranging from hours to weeks depending on the moon, trying to maintain human circadian rhythms on worlds with very different day lengths would require completely artificial light-dark cycles inside habitats, ignoring the natural planetary cycle. This creates situations where habitat interiors maintain 24-hour cycles while outside conditions don't match. On the moon, you'd experience 2-week-long days and 2-week-long nights while trying to maintain normal sleep-wake cycles inside. This dissociation between internal scheduling and external environment could be psychologically disorienting and might cause health problems similar to permanent jet lag. We don't have long-term data on how well humans can maintain circadian synchronization under such conditions. Space habitats without planetary day-night cycles at all would need to impose completely artificial 24-hour lighting cycles. This is feasible, but creates environments totally disconnected from any natural cycles, potentially psychologically problematic. As humans evolved in environments with natural rhythms, the absence of seasons and natural day-night cycles could contribute to psychological problems in space settlers. Speaking of seasons, humans also adapted to Earth's seasonal cycles driven by axial tilt and orbital position. These create predictable annual variations in day length and temperature and food availability that shaped human evolution and that continue to affect human physiology and psychology. Seasonal affective disorder shows how some people are particularly sensitive to seasonal light changes. Annual rhythms in reproduction and immune function and metabolism are documented across human populations. Other planets have different seasonal patterns or no seasons at all. Mars has seasons due to axial tilt, similar to Earth, but each season lasts about twice as long due to longer orbital period. The Moon and many other bodies have negligible axial tilt, creating no seasons. Living without seasonal variation might affect human health and psychology in ways we don't fully understand. The complete absence of natural environmental rhythms could be psychologically destabilizing for some individuals. So circadian and seasonal mismatches create another layer of biological incompatibility between humans and non-Earth environments. We're adapted to Earth's specific temporal rhythms, and disrupting these causes health and psychological problems. Maintaining these rhythms artificially in habitats creates environments disconnected from the natural planetary cycles, which itself might be problematic. Our biology expects certain temporal patterns because we evolved under those patterns, and changing them has consequences. Now let me examine the psychological and social dimensions of abandoning Earth, which are perhaps even more severe than the physiological barriers because they affect mental health and social cohesion and cultural continuity in ways that make permanent off-world settlement psychologically unsustainable for general populations. Humans evolved as social creatures living in groups within natural environments. Our psychology is adapted to specific environmental conditions and social contexts that are difficult or impossible to replicate in space habitats. Consider the sensory deprivation of living in artificial enclosed environments. Humans need exposure to natural environments for psychological health. Studies consistently show that access to nature reduces stress, improves mood, enhances cognitive function, promotes physical activity, supports immune function. Even just viewing natural scenes or having plants indoors provides measurable benefits. Space habitats are completely artificial, metal and plastic, and controlled atmospheres, no weather, no wild spaces, no horizons, no natural landscapes. Everything is engineered and enclosed and limited. This environmental monotony and artificiality would be psychologically damaging over time, especially for children who would grow up never experiencing Earth's natural environment, never feeling rain or wind, never seeing wild animals or forests or oceans, never experiencing the sensory richness and variability of natural environments. The psychological impact of this deprivation is unclear, but likely negative. Anecdotal reports from people in isolated environments like submarines and polar stations consistently mention psychological stress from the artificial, monotonous environment. The confinement and lack of privacy in space habitats creates additional stress. Even relatively large habitats for thousands of people would be small compared to cities or towns on Earth. You'd live in close proximity to the same people constantly, with limited privacy and limited ability to get away from others. Interpersonal conflicts that might be minor irritations on Earth become serious stresses when there's no escape. Personality clashes and social tensions have no release valves. This is recipe for psychological breakdown and social dysfunction. Research on Antarctic stations, submarines, spacecraft, and analog isolation studies consistently shows psychological problems emerging over months of confinement: depression, anxiety, interpersonal conflict, cognitive decline, motivational problems, sleep disturbances. These problems worsen with duration and with smaller group sizes and with greater isolation from outside contact. Extending this to permanent multi-generational settlements raises serious questions about whether psychologically healthy societies can be maintained under such extreme conditions. You're asking people to live their entire lives in conditions that cause serious psychological problems, even for carefully selected trained individuals on temporary assignments. The social structure of small, isolated communities also tends toward authoritarianism and social rigidity because coordination and cooperation are essential for survival, and there's limited tolerance for dissent or deviance. Throughout history, isolated communities have often developed oppressive social structures with strict hierarchies and limited individual freedom. Space habitats facing continuous survival pressures would likely show similar tendencies. This creates ethical concerns about the quality of life and individual rights in off-world settlements. Cultural continuity is another concern. Maintaining complex culture and knowledge across generations requires education systems and cultural transmission mechanisms and access to broader civilizations' accumulated knowledge and culture. Small, isolated communities often lose cultural complexity over time as specialized knowledge is forgotten and cultural diversity diminishes. Without continuous connection to Earth's vast cultural resources, space settlements might experience cultural impoverishment with loss of languages, arts, specialized knowledge, diversity of perspectives. Children born and raised off-world would have fundamentally different life experiences and worldviews than Earth-born humans. They'd never visit Earth or experience its environment. Their entire universe would be the habitat and whatever limited off-world environment they could access in suits. They'd be psychologically and culturally alien to Earth humans despite being biologically similar. The divergence between Earth-based and space-based populations would grow over generations, creating populations that might not recognize each other as belonging to the same humanity. The existential questions facing space settlers would be profound. Why are we here? What's the purpose of maintaining this artificial existence isolated from our ancestral home? What meaning does life have in an enclosed artificial environment utterly dependent on technology? Without clear answers, these questions could undermine social cohesion and individual motivation. People might lose the will to maintain the settlement or might experience existential crises that destabilize society. So psychological and social barriers create serious questions about whether humans can actually live psychologically healthy, fulfilling lives off-world across multiple generations. The environmental deprivation and confinement and isolation and social pressures might make permanent space settlement psychologically unsustainable, regardless of solving the physiological challenges. Our minds, as well as our bodies, evolved for Earth, and removing us from Earth creates psychological problems that might be as serious as the biological problems. Now let me discuss a rarely considered but critical factor, which is the developmental biology of humans and how Earth's environment is necessary not just for adult survival, but for proper development from conception through maturity. Human development is an extraordinarily complex process where genetic programs interact with environmental inputs to produce the adult organism. These environmental inputs include gravity, temperature, atmospheric composition, nutrition, sensory stimulation, social interaction, countless factors that must be within certain ranges for normal development to occur. We've never studied human development from conception to maturity in anything other than Earth gravity. We have no data on whether human embryos and fetuses can develop normally in microgravity or reduced gravity. Animal studies show that some species can reproduce in space, but with higher rates of developmental abnormalities and failures. Mammals are particularly sensitive to gravitational variations during development because skeletal and muscular and cardiovascular systems all depend on gravitational loading to develop properly. If humans reproduced off-world in low gravity or microgravity, the resulting children would likely have serious developmental problems. Weak, underdeveloped skeletons and muscles from lack of gravitational loading during growth, cardiovascular systems not adapted to pump against gravity that might fail or function poorly if the child ever experienced normal gravity, vestibular system development problems from lack of normal gravitational reference affecting balance and spatial orientation, potentially other organ system problems that we can't predict because development is so complex and interconnected. These children would be adapted to their low gravity environment but unable to function in Earth gravity. They'd be physiologically distinct from Earth humans, essentially a different population that couldn't intermix with Earth populations without serious health consequences. This creates ethical problems about deliberately creating humans who are confined to artificial environments for life and who can never visit their species' homeworld. Is it ethical to have children knowing they'll be physiologically trapped in space, unable to return to Earth? Beyond gravity, other environmental factors affect development. Radiation exposure during pregnancy and childhood affects brain development and increases cancer risk. The closed artificial environment of space habitats provides limited sensory stimulation compared to Earth's rich, varied environments, which could affect cognitive and psychological development. Limited social environment with small populations reduces social learning opportunities that shape social cognition. Dietary limitations might affect development if nutrition isn't perfectly balanced. The combination of all these factors means that children conceived, born, and raised off-world would likely show developmental differences from Earth children even if gross abnormalities are avoided. They'd be shaped by their environment in ways that make them adapted to space but potentially maladapted to Earth. Over multiple generations, these differences would accumulate, creating populations that are increasingly divergent from Earth humans. This raises profound questions about identity and continuity. If humans born and raised off-world are physiologically and psychologically different from Earth humans, are they still human in meaningful senses? Do they share our values and perspectives and experiences enough to maintain cultural and ethical continuity, or do they become something else, post-humans or space-adapted humans that are descended from us but alien to us? And if so, does establishing space settlements constitute humanity abandoning Earth or humanity going extinct on Earth while being replaced by descendant species adapted to space? These are not just philosophical puzzles, but practical concerns that affect whether space settlement is desirable or ethical. If the price of space settlement is creating populations that are no longer recognizably human or that suffer from developmental problems and health issues and psychological difficulties, then space settlement isn't extending humanity into space, but rather creating suffering and ethical problems that might not be justifiable. So, developmental biology creates another barrier to abandoning Earth. We need Earth's environment not just for adult survival, but for proper development from conception through maturity. Reproducing off-world creates serious risks of developmental abnormalities and creates populations that diverge from Earth, humans becoming something else. The biological continuity we think of as humanity might not survive transfer to non-Earth environments across multiple generations. Now, I want to explore in much greater depth the profound implications of humanity's permanent biological confinement to Earth, examining what this means for how we understand ourselves, our place in the cosmos, and our responsibilities and possibilities as a species. The realization that we cannot abandon Earth is not simply a technical limitation or a temporary constraint waiting to be overcome through better technology. It's a fundamental truth about what humans are. We are Earth organisms, products of this planet's specific evolutionary history, inseparable from the biosphere that produced us and continues to sustain us. Understanding this truth requires completely reframing how we think about humanity's cosmic context and our future. Let me start by examining the concept of human nature and identity in light of our permanent connection to Earth. For centuries, Western philosophy has tended to view humans as rational minds or souls that happen to occupy biological bodies, implying a kind of dualism where our essential nature is separate from our physical embodiment. This perspective makes it easy to imagine that we could transfer our minds to new substrates like computers or robots, or that we could radically modify our bodies to adapt to alien environments while maintaining essential human identity. This dualistic thinking underlies much space colonization advocacy, the assumption that we can separate humanity from biological humans and preserve it in post-biological forms or in heavily modified organisms. But modern biology reveals that this dualism is false. We are not minds inhabiting bodies, but are embodied creatures, where mind and body are inseparable. Consciousness emerges from specific biological substrates and processes that evolved on Earth. Our thoughts and experiences and values are shaped by having human bodies with human sensory systems and human nervous systems and human endocrine systems all operating in Earth's environment. Remove those biological substrates or change them fundamentally and you don't get the same consciousness or identity in a new form. You get something different that might be descended from humans but isn't human in meaningful psychological or experiential senses. This means that preserving humanity requires preserving human biology in environments where human biology can function properly, which means Earth or artificially created Earth-like environments that are so extensive and complex that they're essentially bringing Earth's environment with us rather than adapting to new environments. We cannot become a post-biological spacefaring species while remaining recognizably human, because being human is intrinsically biological and intrinsically tied to Earth conditions. Consider what would be required to genetically engineer humans to tolerate Mars, gravity, and radiation and atmospheric conditions without protective equipment. You'd need to completely redesign skeletal and muscular systems to function in 0.38 grams, which would make them non-functional in Earth gravity. You'd need to redesign cellular DNA repair mechanisms and add massive redundancy to tolerate high radiation, changing fundamental cellular processes. You'd need to change respiratory and circulatory systems to extract oxygen from Mars's thin CO2 atmosphere, or to tolerate low pressure, requiring changes to lung structure and blood chemistry and metabolic processes. The accumulated changes would be so extensive that the resulting organism would be physiologically different from humans in almost every system. It would be a post-human species adapted to Mars, but unable to interbreed with Earth humans, unable to visit Earth without suffering serious health consequences or death, having different developmental processes and potentially different cognitive and psychological characteristics because of the intimate connection between body and mind. This Mars-adapted organism would be descended from humans, but would not be human, and creating such organisms wouldn't constitute humanity colonizing Mars, but rather humanity engineering replacement species for environments we can't survive in ourselves. Some transhumanist advocates embrace this outcome, arguing that evolution and modification of humanity into diverse post-human species adapted to various environments is desirable and inevitable, that clinging to current human biology is conservative and limiting, that we should enthusiastically pursue transformation into whatever forms are advantageous for different environments and purposes. But this perspective ignores the profound loss involved in such transformation. Human culture and values and experiences are all grounded in shared human biology and psychology. Post-humans with radically different bodies and brains would likely develop different cultures and values and experiences. They'd be alien to us even if descended from us. The diversity of post-human species would fragment humanity into isolated populations that can't intermix genetically or culturally. The common human heritage would be lost as each population diverges according to its environment and evolutionary pressures. Eventually, these populations would have nothing in common except distant ancestry. They'd be as different from each other as humans are from other primate species. This isn't extending humanity into space, but replacing humanity with a collection of post-human species. Humanity, as we know it, goes extinct, even as our descendants persist in modified forms. So the biological trap isn't just a matter of practical difficulty, but touches on fundamental questions of identity and continuity. What are we trying to preserve when we talk about humanity's future? If the answer is human biology and psychology and culture as we know them, then we're trapped on Earth, because those things can't exist elsewhere without artificial recreation of Earth's environment. If the answer is merely genetic descendants, regardless of how different they become, then we could engineer post-humans for space, but we've abandoned humanity, not preserved it. This leads to reflection on what makes Earth special and why our connection to it is so profound and permanent. Earth is not just a convenient location that happens to have the resources we need. It's the only place in the universe where human biology makes sense, where our bodies and minds function as they evolve to function, where we can exist without constant artificial life support, where we can experience the environments and conditions that shaped our evolution and that our psychology expects. Earth's biosphere isn't just our habitat, but is literally part of us. The oxygen we breathe is produced by photosynthetic organisms. The food we eat comes from plants and animals that are part of Earth's ecosystems. The microbes in our bodies and on our skin are Earth microbes. We are embedded in and dependent on Earth's web of life in ways that go far beyond simple resource extraction. Ecologically, humans are keystone species in many ecosystems, apex predators in some contexts, major ecosystem engineers through agriculture and land use. We've shaped Earth's ecosystems for millennia, and they've shaped us. This coevolution has created deep dependencies where we need Earth's biosphere, and parts of Earth's biosphere have adapted to human presence. Removing humans from Earth to space would break these ecological connections. We'd need to artificially recreate enough of Earth's ecological complexity to support ourselves, but we don't fully understand ecosystem dynamics well enough to know what minimum viable ecosystem is needed. Biosphere 2 attempted to create a closed ecosystem supporting humans and found it extremely difficult. Oxygen levels dropped due to unexpected microbial activity in soil. Carbon dioxide accumulated. Species went extinct. The system was unstable and required external intervention to maintain. This was with Earth's biosphere right outside, providing lessons and backup. Scaling this to space where Earth's biosphere isn't accessible for reference or rescue is far more challenging. The complexity of Earth's biosphere is staggering. Millions of species interacting through countless pathways of energy and material flow. We've only cataloged a fraction of Earth's biodiversity and understand a tiny portion of ecological interactions. Trying to recreate even a simplified version of this complexity in space. Habitats faces the problem that we don't know what we don't know, what species and interactions are essential versus optional, what simplifications are safe versus catastrophic. Ecosystems are complex adaptive systems that can collapse suddenly when key species or processes are lost. We can't predict which changes will trigger collapse. So Earth's biosphere is not just a resource base, but is the only functioning ecosystem we know of and the only one we fully depend on. Attempting to replace it with artificial simplified ecosystems in space is extraordinarily risky because we don't understand ecosystems well enough to design reliable ones. We're tied to Earth's actual biosphere, not just to the concept of biospheres in general. Attempting to abandon Earth means attempting to abandon the only